Let's do this. Astronomy Cast, episode 375, The Search for Life in the Solar System. Welcome to Astronomy Cast, our weekly cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Morgan Rehnberg, a graduate student in the Department of Astrophysical and Planetary Sciences at the University of Colorado at Boulder. Hey, Morgan, how you doing?
Hey, Fraser, it's good to be back.
Good to be back here. We seem to do this every year. So it's been around a year since you joined me on Astronomy Cast, and we did a very special episode of Astronomy Cast about Saturn's rings. This time around, we are going to be doing a different show, still about ice and water, about the search for life in the solar system, or the search for water in the solar system, and then therefore life. So. But we are doing this episode as part of the CosmoQuest 2015 Hangout-a-thon. So if you're listening to this show, we are still taking donations for the Hangout-a-thon. We're still going to be doing it for weeks and months after the show itself. So even though it's probably been a couple of weeks since the Hangout-a-thon happened, you can still participate. So just go to cosmoquest.org/hangout-a-thon, and you can give some donations to help us keep all of the educational and outreach activity that we do on the air, and we really appreciate it. Okay, so here's what we're going to talk about. With the discovery of water ice in so many locations in the solar system, scientists are hopeful in the search for life on other worlds. So Morgan Rehnberg returns to Astronomy Cast to explain the best places we should be looking for life. All right, Morgan, so your day job, graduate student, what do you do?
Yeah, so I study the rings of Saturn as part of NASA's Cassini mission. And Cassini's now been in orbit about Saturn for going on 11 years. It's hard to believe that we've been studying Saturn that long, but every time we look at something, we discover something new. And so we've got at least 2 more years, or around 2 more years left in the Cassini mission. And we've packed them full of exciting planned observations to help us understand the planet, the rings, but also the moons of Saturn. And as we'll find out, the moons of Saturn are some of the most exciting places in the solar system.
Very cool. So specifically, you look for very small pieces of water ice, but we're going to be talking about maybe some larger chunks of water here. And so, to sort of set the stage here for what we're talking about today, wherever on Earth we find water, we find life. We find it in Antarctica. We find it in the hottest places, in pools of super hot water. We find it in the cooling towers of nuclear reactors. So, why is water what, astrobiologists are really looking for as they sort of look around in the solar system?
Right, so there's not a lot of things that all life on Earth has in common. In fact, we really can identify 2 things that all life on Earth has. One is it's based on carbon. So we call these things based on carbon organic compounds. And as far as we can tell, all the life that we've discovered here on Earth is based on carbon. Fortunately, carbon is one of the most common elements in the universe, and it's often combined with hydrogen, the most common element in the universe. And so we're not lacking for carbon on Earth, and we're really not lacking for it out there in the solar system. The other thing is water. And again, water, we call it H2O, is made up of hydrogen and oxygen, 2 of the most plentiful elements here in the solar system. And it seems like every living thing on Earth needs water in some part of its life process. And water is a remarkably fascinating molecule itself that has properties that are very rare amongst other chemical compounds. And this makes it sort of uniquely suited to help facilitate the processes that life needs. And so because life here on Earth seems to require carbon and require water, that's what we're stuck looking for out there in the solar system. It could well be that life could survive with other things, but we wouldn't know what it would look like, and so it'd be difficult to know how to search for it.
Yeah, it feels like it's the low-hanging fruit, right? Know what life will require. but we do know, like, we don't know what life might look like as we don't understand it, right? So we can only look for life really as we understand. Now, I know NASA has sort of put some theories together about, like, maybe there could be life that might use ammonia as a as a place for the chemicals to mix together, or maybe it might use liquid, trying to think, like liquid nitrogen, like there's different kinds of things could act as a solvent, but we then wouldn't really know what kinds of things would be happening. So water, we understand, we find it here, so we might as well look for water in the solar system and life that's based on that. Maybe if we exhaust that, then we can go through other kinds of chemicals and other solvents. So
yeah.
So go ahead. So what are the good candidates then for water that we may find not here on Earth?
Right. So if you go back 50 years, it seemed like the solar system was a really dry place. We knew that there was water here on planet Earth, and we knew that there was likely water trapped in the polar ice caps of Mars. But other than that, anywhere that we seemed to point our telescopes seemed to be pretty devoid of water. But as we've sent spacecraft to more and more places in the solar system, we've started to find water almost everywhere we look. We found it in craters on the moon. We found it in craters on Mercury. We found it in asteroids. We found evidence for water in meteorites that come back and land on the Earth. And so now it suddenly seems like water is plentiful in the solar system, as long as you know the right places to look. But not all life, we think, not all water is probably equally capable of supporting life. The key is you need liquid water. And in order to have liquid, you need pressure. And so you need an atmosphere or something solid to keep the water in liquid form. Otherwise, water that's in liquid will just evaporate out into space and it'll float away and be lost forever. And so although we see water on the moon and we see it on Mercury, those aren't places that we really want to look for life out there in the solar system, because that is very, very cold, very icy water and not good for supporting life.
Yeah, and this is part of the problem with even Mars, that the pressure on the surface of Mars is super low, that you're never going to get pools, lakes of water, oceans of water on the surface of Mars. You're going to be looking for places that are, as you say, under pressure, potentially deep underground.
Right. So Mars might have been a good place for life to exist billions of years ago. And Venus likely also was a good place for life to have existed long ago, before it got extremely warm. But today, neither of those places are likely locations, I think, for us to find life alive today. We might be able to find the record of past life on Mars if we're particularly lucky, but the odds of finding actual living organisms on Mars today are very low. And it turns out actually that Earth is the only planet in the solar system that seems like it's likely to support life today. In order to find other places that we might be interested in, we've got to look to the moons. And the moons, especially of the outer planets, are some of the most fascinating locations in the whole solar system. And the one I think people are probably most excited about today is the moon Europa. And this is the second of the 4 Galilean moons of Jupiter. So the Galilean moons are the 4 large moons. They're all about the size of Earth's moon that were first discovered by Galileo back in the 1600s when he first pointed his telescope at Jupiter. And they orbit extremely close to Jupiter. And so Jupiter exerts very strong tidal forces on them. And of course, we're very familiar with tides here on the Earth. When the moon passes over an ocean, it lifts that water up and causes high tide. And when it goes to the other side of the Earth, that water falls back down and creates low tide. The same thing happens at the Jupiter system, but instead of having an object the size of the moon, you have the largest planet in the solar system. And so it can actually lift up not just water on the surface, because of course there isn't water on the surface of these extremely cold bodies. It can lift up the surface itself. And as the surface rises and falls, it rubs and scrapes against itself. This creates a lot of heat. And this heat can actually melt the interior of these moons. And so the closest moon to Jupiter, Io, is the most volcanically active place in the solar system, because we have all this molten rock that forms magma and then bursts out of Io. But if you go one moon further out, you get to Europa. And so the stresses there are not as strong because it's farther away from Jupiter. And so it's not enough to melt rock that's probably at the core of Europa. But it is enough to melt the water. And we have pretty good evidence now from the Galileo spacecraft, which orbited Jupiter from 1995 to 2003, that there's an ocean of liquid water underneath the surface of Europa that's probably equal to or greater than all the oceans and rivers and lakes of water here on planet Earth. And so we're talking about a truly vast amount of water. But it is different than on Earth. It's extremely salty, so much saltier, we think, probably, than even the Earth's oceans. But more importantly, it's trapped very far beneath the surface. We really don't have a good idea how deep it is, but most scientists would probably quote you something like 10 kilometers plus or minus 5 kilometers.
Yeah,
so we're talking about very deep, no matter how deep your number you choose to be, much deeper down than the average depth of Earth's oceans are today.
And so, that depth means that, any way that we could try to get at it, to try and actually drill down is, we probably would have a really hard time getting that far down through the ice here on Earth. So to send a spacecraft capable of getting down through that amount of ice and to try and probe the water below is going to be pretty tough.
Right. So we have to try to understand the oceans of Europa to begin with indirectly. And there's a couple of interesting ways that we can do that. For one, there's the idea that there might be giant plumes of water, like geysers of water, shooting out of the surface of Europa. And there's been sort of some circumstantial evidence from Hubble to suggest that this might be the case. But the reason people really think that this could happen at Europa is because we see it one other place in the solar system, and that's a moon of Saturn called Enceladus. Enceladus also has a localized ocean of liquid water beneath its south polar region. And that water builds up in pressure and somehow bursts forth through cracks in the surface of Enceladus to then shoot about 200 kilograms of water out of the surface of Enceladus every second. That's enough to fill up a few Olympic-sized swimming pools every day. So not a trivial amount of water that's escaping. And it's enough water to create the entire E-ring of Saturn, which is the largest ring of Saturn and one of the largest rings in the solar system. And so we know that underground oceans can connect to the surface through geysers. And that's great because it allows us to study them without actually having to go into underneath the surface and find out what's there. We can just wait for things to squirt out and then fly our spacecraft by those and either take pictures or collect some of those particles or make other kinds of observations. Europa also has these large cracks on the surface that could be related to the stresses of this tidal interaction with Jupiter. And it's possible that at times these cracks are deep enough that water from underneath the surface from within the ocean of Europa can actually leak up to the surface. And this would allow us to land on the surface and study that top level of ice that could be formed based on water that was somewhat recently in the ocean of Europa and get a better sense. And these cracks play another important role because it's not just carbon and water that all life on Earth needs. It also needs energy. And humans get energy by eating food. Plants get energy by doing photosynthesis to turn the light of the sun into energy that they can then use to grow, that we can then use to pick them and eat them. You can also get energy, say, from hydrothermal vents. This happens at the bottom of the ocean. And really, you can also get energy from the combination of certain chemicals that react, like dropping, for example, sodium in water releases a lot of energy in that reaction. And these are sources of energy then that these animals or these creatures could use different places in the solar system. And these cracks are a great way to get that because remember, these volcanoes on Io are shooting up tons of ash. And as this ash deposits onto the surface of Europa, and we're pretty sure that it does, these cracks offer a way for that ash to sink down into the ocean. And this could provide a source of organic material that then forms the basis for the actual structures of life, but also support or infuses the oceans with some unique chemicals. And these chemicals could react with the salts and the rock at the bottom of the ocean to provide some of the energy needed for microbial life to exist within these oceans.
So could the ash that we see on the surface of Europa, could that help explain some of the coloration that we see on Europa?
Yeah, it's likely that what astronomers often term as brown gunk is at least partially material that's fallen from Io, from the volcanoes on Io, onto Europa. And the surface of Europa is extremely young. It's one of the youngest surfaces in the solar system, just millions of years old, as opposed to, say, the moon's surface, which is billions of years old. And that means that the surface must be getting recycled relatively frequently. And when that happens, anything on the surface is going to get kind of sucked down into the moon. And that would allow it to recombine with material that's already in the oceans to enrich those oceans with more complex chemicals, more complex molecules that could then form either the basis for life or the food source for life or some combination of those.
That's really cool. I hadn't heard about that research. That's really kind of amazing. It's often I ask the questions and I kind of already know the answer, but I actually had no idea that was one of the explanations. It's great to have a planetary scientist here on Astronomy Cast every now and then. So you've got this situation, right, that the cracks on Enceladus are potentially materials falling down, and then they're almost like they're subducting. It's like what happens with the plates on Earth, right? That you've got the ice potentially crossing on top of each other and cracking open, and things going back down, and a way for the material to cycle down into the water. So now you mentioned Europa, and sort of as one of the classic places that we want to look because it's potentially got this energy source, it's got this water, although it's fairly salty. But how is Enceladus as a place for life?
Enceladus has, water going for it, and it has heat, a lot of heat, in fact, in the South Polar region of Enceladus, more heat than we can explain through any source that we understand. So if you consider radioactive heating, so the breakdown of elements like uranium releases heat naturally in the crust of the Earth, also in pretty much every body in the solar system. And Enceladus also experiences tidal heating from Saturn. It's much farther from Saturn than Europa is from Jupiter, so this heating is much weaker. But if you combine these, you don't get nearly as much heat as we observe coming out of Enceladus. So there's some incredible source of heat providing this localized region of Enceladus with a lot of energy. And so we have energy and we have liquid water because of that. The rub with Enceladus is it's difficult to know where you get the organic compounds that you need to sustain life, because there's not like an Io around Saturn that's spewing out all of these kinds of compounds. And when we look at the water coming out of the ocean, the plumes of Enceladus, they're almost perfectly pure water. We see some salts and things within them that we know are sort of act as an antifreeze to keep the ocean from freezing, even given this tremendous heat. But we don't see a lot of more complicated compounds. And some of that's because they're heavier and therefore they don't fly out as far from the surface when these geysers erupt. But also it's likely that there's just a lot less organic type material at Enceladus than you would find, say, at Europa. And so I think that probably makes Enceladus a second-tier candidate in comparison to Europa for the possibility of having this ocean.
Yeah, and that level of saltiness, I mean, there are places on Earth that have higher levels of salinity that they have found life. There's very salty pools. They found life on Earth. So it's not a deal killer.
No, it's not.
No, but I mean, it turns out like Europa is definitely one of the best candidates, but the other Jovian moons seem to have under I guess ice crusts and internal oceans as well, right? I mean, Ganymede, Callisto, there's something going on there.
We think that Ganymede and we suspect that Callisto also have oceans of liquid water underneath their surface. Because they're further out than Europa, they don't receive nearly as much tidal heating from Jupiter as does Europa. And so probably these aren't either as warm or as large, and they could be more irregular in how capable they would be of supporting life. And so pretty much anything that Europa or anything that Callisto or Ganymede has, Europa has better. And so if you're going to play the odds game and say, well, what's the most likely place in the Jovian system to look for life, it's definitely Europa. It's the closest to Jupiter of the three. It's the closest to Io of the three. Its surface shows sort of the most remodeling, and therefore the youngest surface. That means most materials being incorporated underneath into the interior of the moon. So if you're going to go to one of those three, you're going to want to go to Europa. And that's exactly what NASA's planning to do in the coming sort of 10 to 15 years.
So I guess one question then is, like, how does the sort of panspermia idea that life could be moving from world to world within the solar system, how does that play into it?
Yeah, that's really important, because there's sort of two questions when you think about life in the solar system. There's the question, could this place support life? And I think the answer is probably yes, Europa could support life. It's likely yes, Enceladus could support life. In fact, experiments we've conducted on the International Space Station suggest that just normal plain Jane Earth bacteria can survive well more than a year exposed to the vacuum of space and then reconstitute themselves into their original living organisms. But in these locations, the conditions are still extremely harsh. And the question is it possible for life to have arisen in these locations? Sure, Europa might be able to support life, but could life be formed in conditions as harsh as Europa? Because even though we see life all over the Earth, whether we're talking about hot volcanic environments or super salty underground lakes in Antarctica, it's not likely that the life we see there formed there. Life on Earth probably formed in some of the most ideal conditions on the planet, whatever those happen to be. And we don't really yet understand what exactly is necessary to form life. But whatever it was, it formed in the best possible conditions on Earth. And then over millions and billions of years, spread to all of the nooks and crannies of the planet. So Europa, Enceladus, they never had probably these nice balmy conditions that would make it most probable that you could form life. And therefore, it's a question of if life has to arrive on that body, probably it's unlikely to see life at Europa or life on Enceladus. But the idea of panspermia, which is that life can travel from world to world within the solar system and within the galaxy, you can kind of sidestep that issue. And there's two ways to think about panspermia. There's the idea of interstellar panspermia, which is that life formed somewhere in the galaxy, and then that world or a chunk from that world was ejected out of its solar system and ended up somehow lumbering into our solar system early in the formation of the solar system, and it basically infected our solar system with life from another star. That is a kind of a speculative way of thinking about panspermia, because there's evidence that dust particles and things move between stars, but it's not the most likely situation in the world. On the other hand, there's the idea of interplanetary panspermia. And this is the idea that life somehow manages to luck into arising on some planet in our solar system. And most people would say that planet was probably Earth, but it could have been Mars or Venus earlier in their lifetimes. And then an impact on the surface of Earth or one of these other bodies jars loose pieces of rock that have this life attached to it that then fly onto other worlds in the solar system and infect them with Earth life. And this is a lot less speculative. It's still, far from an accepted idea, but we know that material moves regularly between the planets in our solar system.
And that life is rugged enough to handle each one of the stages, right? That you can go from, an asteroid striking Earth and striking up Mars, for example, and throwing up all that material. Life can survive that process. Life can survive time spent inside a meteorite in space, and life can even survive the re-entry process of coming back through to a new planet.
That's right. Of about 60,000 meteorites that we found on Earth, more than 100 we know came from Mars. And models that sort of simulate this suggest that the transfer of material from Mars to Earth happens quickly. Not millions of years, but thousands or tens of thousands of years for these sorts of things. And that seems like a long time, but in the span of the solar system, that's the blink of an eye. And while we don't have confirmed samples from Mercury or from Venus, it's not out of the question that we have, or there could be meteorites from those worlds here on Earth. And it's even more likely that those worlds have Earth and Mars meteorites that were blasted off of those planets, fell in towards the sun, and happened to land on Venus or on Mercury. It's a little bit trickier to get those things out into the outer solar system, but it's not impossible. And this would enable life that arose in sort of, quote, comfortable environments on Earth or on a warm, wet Mars to travel to one of these places capable of supporting life, but not capable of forming it. And we'll kind of have an idea if this happened, because if we manage to find life on Europa or Enceladus or Titan or any of these other places, and it looks anything at all like Earth life, that will be strong support for the idea of panspermia. Because, the chances of life arising independently in two places and looking similar, while certainly possible, are probably not particularly high. And so this gives us a clue of whether or not it's possible we're able to find life.
Sorry, you cut out for me there, Morgan.
Yeah, sorry, we both cut off, yeah.
Yeah, but you can hear me now?
Yep.
Okay, all right. Sorry, Preston. We'll keep moving. All right, so now one of the things, I guess we've talked about Europa, we've talked about Enceladus, we've talked about this, but in fact, the new research says that it really feels like there's probably liquid water in a lot of even the Kuiper Belt objects, because potentially these have some radioactive heating inside of them, right? And so you could get liquid water on Pluto or Sedna.
It's possible. Radioactive heating is more effective on larger bodies, and it's more effective early in the history of the solar system than later on, because you start with a finite amount of uranium and plutonium and these other radioactive elements, and there's no way to replenish them. And so you start off with a lot and you start using them up, and over time you use them up, and the heat you generate is less and less over time. And of course, if you're a larger body, you're going to start with more, and so you can more effectively heat the interior of yourself. And so I think that we would be even less likely to find life in one of these far off isolated bodies than we would somewhere in the inner solar system, where we have all of these additional sources of heat. We have tidal heating, we have temporary heating from, say, large impacts that could have been very important at the beginning of the solar system. And we have light. And light not only heats the surface, but it's a form of energy that we know life here on Earth has harnessed extremely effectively. And light is something that is almost non-existent when you get out past the orbit of Neptune. Jupiter receives about 4% as much light as does planet Earth, and Saturn receives 100 times less light than does the Earth. And every time you go out a planet, it drops off precipitously. And so light on Earth is sort of the basic energy medium that we collect most of our energy here from on the surface. And it does warm the surface of our planet. It warms the surface of Mars and Venus and Mercury. And that just doesn't exist in the outer solar system. And so while it was possible that some Kuiper Belt objects supported oceans maybe early in the solar system, and some that either had sort of exceptionally large concentrations of radioactive elements or were exceptionally large might still support those oceans today. The isolation that they experience, I think, is a major impediment. You don't, sort of in the same way that Enceladus is, you don't have a source of organic material. So even if you started off with some, you're going to expend that in the chemical reactions needed to sustain life. These bodies tend to be relatively small, and so they just don't start off with a whole lot of material. And unfortunately, even if life is out there, they're too far away for us to get to. New Horizons plans to fly by a Kuiper Belt object something like 3 or 4 years after it passes Pluto. And of course, we know it took 9 years to get from Earth to Pluto. And so we're not in a position to study a selection of these objects that is large enough to have a good chance of finding life. We'd be much better off trying to drill through the surface of Europa or peer into the oceans of Enceladus or land on Titan than we would going out, I think, to the Kuiper Belt.
But do you think, with all of these kinds of plumes, the plumes that are coming out of Enceladus, potentially the plumes that are coming out of maybe even Ceres, but also Europa, potentially, you've got this opportunity where maybe the chemicals, the constituents of life is actually being ejected out into space, that you could fly a spacecraft through it or near it and try to, take a whiff as you pass through it. I mean, is there potential there?
In a way, there is. One of the more interesting places that has what we think is a lot of organic compounds are comets. And comets are endemic to the outer solar system. And so this could suggest to us that Kuiper Belt objects have more organic material than we sort of previously considered. And we've made some efforts in the last decade to try to understand comets as a source for these organic compounds. Some people think that comets hitting Earth delivered organic compounds to Earth. This would work. We know comets hit all of the inner solar system objects early on in the history of the solar system. And so we've been trying to study comets in more detail. We flew through the tail of a comet about 10 years ago with the Stardust mission. And just, of course, in the past year, ESA's Rosetta spacecraft and Philae lander have approached very close to a comet and have been studying it in sort of unprecedented detail. And we know from these observations that the tails of comets, the surfaces of comets do have organic compounds on them. And so it could be that comets themselves are possible locations for harboring life over long periods of time. Now, they're not warm enough probably to sustain sort of ongoing liquid water, but if they came from an object that ever had life and ever had liquid, they're kind of buses bringing this life around the solar system and randomly hitting into things and depositing its passengers along with it.
So space whales, do you think, on Europa?
Oh, space whales would be nice, but I think there's nowhere in the solar system that we should expect to find anything other than microbial life. The amount of energy that it takes to sustain macroscopic life here on Earth is tremendous. If you look at the food chain for any animal, you need an incredible amount of organisms below it. Just think about a cow, for example. Cows have to eat a tremendous amount of grass. And the Earth is basically covered in grass and trees and leaves and things like that, just to support a relatively small, in comparison, population of animals. And so I think at best we'll find microbial life that's well suited to living off the land in these extremely harsh environments. And that's the life that we see living in these super salty lakes, in these caves far from the reach of sunlight, places we see lots of pressure, like living underneath the surface of the Earth. All of these are microbial life. That's what we should be looking for and expect to find, at least in our own solar system.
Well, we should, I guess, if people are like watching all the missions that are happening, what are some upcoming missions that are going to help us maybe push these questions a little forward?
Absolutely. So, ongoing missions right now that will help us understand these questions are Rosetta, studying Comet 67P, and Cassini, which will continue to observe Enceladus and other moons of Saturn that could have similar features as Enceladus. But as we look forward, probably the most exciting mission coming up is the Europa Clipper. A mission whose name will probably change before it actually launches. But the idea here is to fly a large sort of flagship level spacecraft to Jupiter, go into orbit about Jupiter, and then make a series of 40 or 50 close flybys of Enceladus or of Europa to study the surface, to try and sample any plumes that might be there, to shoot radar down through the surface to try to get a range on the depth of that ocean, and possibly even to deploy a lander to the surface. And then on Mars,
with support from the Europeans, if we're lucky.
With support from ESA, if that works out. And then on Mars, sort of what we're working up to is a sample return mission. And so Curiosity has been searching Mars for understanding the large distribution of chemicals on the surface and what kinds of rocks are made up of what compounds. And then the next spacecraft that will sort of advance this is a spacecraft that should launch in the early 2020s called MAX-C. And what MAX-C is going to do is it's going to collect samples of the surface of Mars and package them up in sort of super tightly sealed containers. And it's going to deploy those in a specific location on Mars. And then a future mission, even beyond MAX-C, is going to land, collect those samples, blast them off, and return them to the Earth. And this will allow us to study rocks directly from Mars that didn't have to travel through thousands or millions of years of space. They didn't have to burn up through the Earth's atmosphere. They didn't have to smack into the ocean or land on land. They come pristine from Mars. And although the odds of finding like fossilized microbes in them are probably relatively low, having those in the lab where we have much, much more sensitive instruments than we do on rovers and landers on Mars, we're going to be able to get a much better idea of the chemical composition of the Martian surface. And that will ultimately lead us to a better understanding of its history and whether Mars was perhaps very Earth-like billions of years in its past.
Well, Morgan, very much for joining me on this very special episode of Astronomy Cast. I think we've got, I mean, really just this question is really just beginning. And I think the best is yet to come. We've got some pretty exciting explorations coming up. So will you join me again in a year from now?
I will indeed. And if we're lucky, we'll have even more exciting news to talk about from some of these searches.
Absolutely. All right. Well, thank you very much, Morgan.
Thank you.
All right. So go ahead and stop your recording.
Stopped, and I will.
And then save it.
Export.
Yeah. And I'll export mine. I'm not going to upload it right now.
Yeah, I think that's a wise.
I'm not going to mess with it. Now, did I cut off at all for you during that?
Just once in the middle when you said that I froze for you, you also froze for me.
Yeah, so it sounds like it was neutral. I'm going to try upping my bandwidth again then, because it feels.
Yeah, other than that, you were quite clear.
Yeah, so things seem like they're working again. So, all right. Well, do you got some time to take some questions from people?
Yeah, absolutely. Looks like we got about 15 minutes. Let's check in here and see how we're doing on our goal for Pamela.
Yeah. Hello.
Oh, we're getting there. Our goal is 13,500 this hour, and we're at 13,100. So you got about 15 minutes here to help us out and reach this goal and get an opportunity to get a meteorite hand delivered by
baby
Fraser Cain, if you happen to live in the west coast of Canada.
Yeah, Vancouver Island, they'll hand deliver it. Otherwise, it'll be in the mail. So I'm giving out. Look at this metal from space.
Gorgeous.
Woo! There's a bunch of them here. Each one is unique. Each one suffered its own terrifying reentry through the Earth's atmosphere, and landed in Argentina about 5,000 years ago. So these are the Campos del Cielo meteorite. These are the these are the they're nickel iron meteorites that landed about 5,000 years ago, and they're the common ones. I mean, you can find these most of the time when you see a metal meteorite. It's one from this asteroid fall. So look at this one; it's very thin.
Yeah,
I got
cool.
Yeah, I got a lot. So each hour, I'm going to give out. We're going to pick at random all the people who donated during that hour, and I will send a meteorite to the one in person live on Vancouver Island. But and also they come with one free hour. So it's telling me that I'm breaking. Oh, so much for high quality. I give up. So it comes with one free superpower. So once you get your meteorite, you have to then tell me what superpower you got.
It's a solid deal, I think. Get a little science done, get a superpower.
Exactly.
What can you ask for?
One of my friends has gotten weather control. He says every time he goes for a ride in his motorcycle, he tends to have good weather. So, yeah, right. No flight yet or super strength, but
I think weather control is underrated. Everybody thinks of invisibility or teleportation or flying, but honestly, just a nice sunny day on demand is probably about the best thing you could get.
Yeah, it would be pretty good. So Tom Nathy asks, given the past history of massive impacts on Earth after life arose, would chunks of Earth get tossed out with bits of life's material on it? So,
certainly chunks of life or chunks of Earth were thrown out into space on or as a result of some of these giant impacts. I think there's no doubt that was the case, and in fact, we expect that the moon is probably littered with Earth meteorites. And there's a certain class of meteorite we find here on Earth, and the name escapes me, but these are actually meteorites that were the result of material being ejected from Earth, floating around in space for a while, and then re-impacting back on our own planet. And that's probably the result that happens for most of the material that's ejected, because Earth is a relatively massive planet, and its gravity is going to suck in most of those objects. But a non-zero amount will escape, and over billions of years, and we've had a lot of big impacts in the history of the Earth, some of that's going to get out there. I think the question that we don't really understand is that's an extremely violent process. Can life survive? We know life can survive when it gets to space, but can it survive being hit by a rock traveling at 80,000 miles per hour, then being blasted up as a fireball probably out into space, and then traveling for thousands of years in space? It's that first part, I think, getting the life off of Earth and into space, that we really don't understand yet and don't have a particularly good way of understanding.
Let's see, what else we got here? Michael Jobin notes that where he lives, the land is covered in cows.
Wow.
So clear. They should send that terrain to Europa, I guess. So Sev Dustbunny says, I've heard it stated by some scientists that life seems to have been almost the ultimate expression of chemistry. What does Morgan think about that statement?
I think that's an interesting interesting sort of eloquent statement for sure. There's an almost infinite variety of chemical reactions that are possible given the 100 or so elements that we find relatively commonly in the universe. But many of the most remarkable ones happen within our bodies and within the bodies of other animals and creatures that we see here on the Earth. Just the fact that, for example, you can take sunlight and directly turn that into energy, into sugar, that then can be consumed as energy is truly remarkable. And so I think that certainly we spend more time studying the chemical reactions in the human body than we do of pretty much anything else. And that's not just because we want to make ourselves better. It's because they truly are some of the most fascinating things in science.
Right. Matt Wood says, Morgan has, what webcam do you have? It has a fantastic quality.
Oh, I have like the nicest Logitech. After Fraser gave me grief for my webcam for a long time, I went out and bought the fanciest one I could to make sure. But I'll tell you, probably what helps more than the webcam is having good lighting. Because these cameras aren't really designed to handle extreme lighting conditions very well. And so to my left and to my right now, I have a pair. In fact, I'll just tip my camera here. Never do this at home. I have a pair of umbrellas that are illuminating me evenly from both sides. And that helps the camera get the best view. Because as we were talking about in the show, light is everything.
Yeah, absolutely. So it's about the lighting. It's about creating good, even lighting on you, and then that allows the camera to sort of not be so grainy. And I've got the same camera, and I've got a similar lighting setup.
Yeah, do you know the name of it here? It's the Pro Webcam C920 by Logitech.
And so I've got the 910. So I've got essentially the same model, but just one release before yours.
Yeah,
it's a great camera. And it's also really actually got pretty good audio on it too. So right now I'm using my fancy Blue Snowball.
Yeah, I got a Blue Snowball and pop filter.
Yeah. But I can switch to there we go. So now I'm using the microphone that's actually on the camera itself. And it's pretty good. It sounds all right.
Yeah, it's a lot better than a lot of webcam cameras.
Yeah. So it's all in one. So if you want to do any outreach and you really sort of up your technical game, go with the 910 or the 920, that high-end version.
About $100, maybe $75 or $100, but it's
and I've seen them on sale sometimes for like $50. So they're not bad at all, and they just are great. So let's see, any more questions?
So you're staying up for a few more hours here. You got to host the Weekly Space Hangout Town Hall.